In this lesson, we're going to focus our attention on appropriate memory allocation policies that can be utilized by the operating system. We've handled how we can implement a broker through hardware, and now what we want to do is focus on appropriate mechanisms that we can do with the operating system for allocating memory for the processes that need to execute. And so with this, we're going to focus on three specific policies or approaches with fixed size partitions, variable size partitions, and we're going to make use of both hardware-based and limit registers. And so you want to consider that whenever you execute a processor, you're telling it how many processes that you'll need to run. And for each process, it's going to need a specific memory size. And so with this regard, we have a partition size that's set up at 5K and 8K. And so the main components that govern the structure for allocating memory are going to be a bit that determines whether it's occupied, the partition size, and the process that is allocated to that memory. And the occupation bit is going to be a 0 or 1. If that specific partition is already allocated, then the occupied bit will be set to 1. And so these are in a general scheme. This is the way that most operating systems would set up the way that set up the partition table. But more efficient mechanisms can be utilized in terms of the structure in allocating the partition. And so with this in mind, we are executing P1, and we've determined that P1 needs 6K of memory. And so you want to keep in mind that the total size is fixed. And so it can be and so is that number of partitions. So in this case, we have 6K of memory needed for P1, but P1, and therefore we'll place it in the partition for 8K. And so what this means is that it will result in 2K that is unused. And so this is representative of what we call internal fragmentation. And so with the internal fragmentation, the 8K partition is used, 6K is actually for P1, and then 2K is wasted. And so calculating that, we have internal fragmentation of 2, which is 8 minus 6. So what if another processor needs to use $6K? And so in this case, we don't have, we have 6K available, but it's not contiguous. And so what that means is that we aren't able to allocate it. And so let's consider another example, what we call external fragmentation, in that we have P1 that is executing and P2 that is executing. And so consider that we have P3 that needs 4K of memory. So is it possible to allocate it? Well, we have the memory that is available, but it's not representative in a contiguous manner. And so are we able to combine the various blocks that are free in memory for use? And since these since memory is being represented using a fixed partition size, we're not able to combine them together in this sense. It will require that the system be restarted and then the partition sizes be reallocated differently. And so this represents external fragmentation in that all non-contiguous free memory partitions represent the total external fragmentation. So with this in mind, we're not able to allocate the memory that process 3 needs. And so now we have 4K of non-continuous memory here, which gives us the 4K of external fragmentation that we have represented. So we want to keep in mind the internal fragmentation is going to again represent the size of the partition, the actual memory used. And external is going to be representative of all non-contiguous free partitions. So what are the benefits that we have associated with fixed size partition memory management? The good thing is that we provided for a mechanism that is that's simple in nature, but the bad news is that it can result in some fragmentation from the representation that we have internally as well as externally. And so let's consider we have a 2K process and a 6K process that's being used. And so here we have 3K unused and 2K unused. And so that is going to be 5K of internal fragmentation. And so here, let's consideration that we have 2K that's being used, and then we have 6K that is being used again. So what's the external fragmentation? And for this, it is going to be 0. So how exactly can we overcome internal fragmentation? We want to be sure that we can allocate exactly what is needed. We want to be able to represent things using appropriate variable size partitions as well. And so how can we accomplish this? So in order to provide for variable size partitions, we're going to include an appropriate starting address. We're going to have a size, and then we're going to have the process ID. And so now let's provide for a variable size memory that represents each process to provide for contiguous use of memory. And so in this way, we're able to provide for a starting address for each process, the size being used, and we're able to provide for variable partition sizes based off of the memory that we need. And so now we need to consider what happens once a process finishes. So now we can see that once it is finished and complete, we'll have 2K available at the beginning and 2K is available at the end. So what happens if we have a new request that needs 4K? Well, in this case, we're going to have a problem because we don't have it available contiguously. And so this results in us having external fragmentation. But let's consider that P2 exits. So in this case now, we have 2K partition and then 6K free, but really that just becomes 8K. And so now the process would be able to execute. And so what are some ways to reduce external fragmentation? There are various algorithms that can be used. You can have a first fit algorithm, best fit algorithm, and next fit algorithm. And for the majority of cases, there are variations in the algorithms, but they all will work well for generalized cases, but there sometimes can be specific cases in which the algorithms might not perform the same. And so another mechanism that we can use is compaction. And in this case, what we do is we can reallocate memory and provide for the ability to move memory around, and that enables free memory to be represented contiguously in memory. So we can then relocate P3 that is executing and create the contiguous space that we could use for future processes that might require more. But this can be an expensive action that occurs. So that is one problem that has to be taken into consideration. And so with variable size partition memory management, there is no external, no internal fragmentation, no fragmentation, both internal and external fragmentation. And really B would represent that we don't have any internal fragmentation with variable size partition memory management. And so with external fragmentation, you can limit the full usage of the memory resources, and you can provide for compaction, but then compaction can be a little bit expensive. And so these are some issues that can pop up. And so how exactly can we resolve these issues? So let's take a look at how our memory footprint is represented. You basically have in an arrangement code, data, heap, stack, and these are all going to be in a nice clump that are represented together. And so what does the system do with this process address space? And what can we do? What modifications can we make to the memory footprint? So we have that our memory footprint is going to look like this. So what if we could possibly store our memory footprint in discontinuous memory locations? And what would be needed in order for us to implement this approach? Well, what we can do is provide for what we call pages. So how could we split each of these processes into different pages? Well, each page is going to be represented as a 4K byte. And we can see here, 1, 2, 3, 4, 1, 2, 4, that we have represented. And this enabled us to use any 4K chunk in order to allocate memory. So in this case, we have memory that's completely full with different chunks. So we've been able to split memory up, but now we need to figure out how we can make use of it. And so what we want to do here is see how we can incorporate a broker that can provide for virtual addresses in this case. And now what we want to do is provide for a broker that can be used to implement things from our contiguous data representation to discontiguous. And so how is the mapping function for this broker going to look? So we need to understand that the broker need to map the virtual address from the CPU to a physical address. And so this is how we have our broker represented. But how will we use it to map from virtual to physical? Well, maybe for this issue, we need to have a type of directory that can be used. And so we'll need to figure out who is going to set up the directory and then who's also going to be able to make use of it. And so again, in this case, what we're going to do is make use of a combination of both hardware and software. And so who's going to set it up? We'll have our operating system. And who's going to look it up? Hardware. And so now the page table is going to need to be accessed and looked up very quickly and very often. And so there are going to have to be some mechanisms that are implemented and put in place in order to allow for this to occur. So first, we need to keep into mind how big is the table that we're going to use with the broker. With this in mind, we want to make sure that we keep a table that's big enough but not too big. So what would be a possible lower limit? So there would be only one entry in the page table. And so that's going to be the same as the base and the limit. But if it's a very big page, it would be mapping the entire address space to just one page. But we consider at the upper limit, we would want to be able to map every word appropriately. And in this case, the table would be represented as the size of the address space times the address size in words. And so that would be us mapping every word to its own page. So would we want the table to be this big? That means it would almost be as big as all of memory, and that would mean that we would need to keep up with a lot of different approaches. So that's not practical. So we have our lower limit and we have our upper limit. And what we want to do is make sure that we choose something that is in between. So we choose a page size that we can map that is going to be representative of at least 1/2 of the last page on average. And with this taking this into consideration, we'll have smaller pages that'll get us a bigger page table and take more CPU time to manage. And you also have to keep in mind that the smaller page tables are going to take up a lot more CPU time. And so you want to keep in mind that page sizes can vary from 512 to 2048 bytes several decades ago. And this was back when memory was a lot smaller. These days, a page size can range from 4 kilobytes up to 1 gigabyte, and they can be set per process. And you want to consider that a page size is always going to be a power of 2. And this allows for a virtual page number to be split, the virtual page number and the offset to be used to split the virtual address space. And so using this, we're able to provide for a mechanism to index into the page, which makes it easier to determine what parts of the address we'll need to look up. So let's keep in mind that the page size is going to be 2 to the n, and the lower n bits are are the offset, and bit in and up are going to be the virtual page number. So let's say that we have a 4 kilobyte page size and a 32-bit virtual address space. So 4 KB is going to be 2 to the 12. So the bottom 12 bits are offset, and the top 20 bits are going to be VPN. So for example, for a virtual address that we have represented, we have initially 4 for the VPN and 4095 for the offset. So once the page table is in use, how can we have it represented? From the user view, we only see contiguous pages, but really the broker is looking up to actually see where it's being stored in memory. And so in this case, we can use the VPN to get the actual entry in the page table. And then the offset is going to tell us the actual physical memory location. And so this address translation will start out with the virtual page number that we have and the page offset. And the page size is essentially going to tell you that what the page is going to be. And so if it's 2 to the n, then it's going to be n bits. And so the number in the page table is going to be called the page frame number. And what we need to do is allocate our memory and then divide it up into frames, and we'll call this page frames. And the page frames are going to be representative of an actual physical space in memory. And so since it's going to be mapped to the actual physical location in memory, we don't have to worry about if it will actually fit. But the broker is able to accomplish the translations that are needed using the virtual address. But you have to consider that the page offset is not going to change. And the page offset from our PFN is going to represent the actual physical address that is being used. And so once we have the physical address that we need to use, that's ready to go out for memory. And so that provides for a straightforward mechanism for appropriate address translations. So let's consider an example. We have a 32-bit virtual address space and a page size of 8K bits. So how big is the page table? We want to consider that the virtual page number is going to be what size? We have 8K is going to be 2 to the 13th. So the bottom 13 bits are going to be representative of the offset. And so the VPN is going to be how many bits? 19. And so with VPN being 19, we know the page table is going to be 2 to the 19th, or it's going to be representative of 524,288 entries. And so that means it's just very important to keep in mind that you know how big the VPN is, and then you can know how big the offset is. So let's consider if we have a 32-bit virtual address and a 24-bit physical address. And we know that the page size is 4 bytes. How many page frames would we have in memory? We have a physical address of 24 bits. And you want to just remember that the offset is the same in both the virtual and physical memory. And keeping that into consideration, what is the biggest that the page can be? So that's going to be 4,096 page frames. And the page table is going to be representative of 2 to the 20th for this example in ours. So if we're able to map that appropriately, we have a 4K page that's going to be 2 to the 12 bytes. So we have a CPU, and then we have our 32-bit VPN virtual address. We have the VPN and the offset. And we need to get to a 24-bit physical address. So we'll need to do a translation. We have 12 bits based off of what we know. So we'll go to our page table that has our page frame numbers available for us. And so we have 20 bits that are available. And so how many table entries are we going to have? We'll have 2 to the 20th. And so once we have the translation to the page frame number, we know that we can make use of the offset, which is going to be the same. And so then we're able to provide for an appropriate mapping to our physical memory. And with this in mind, we know how many frames, page frames, are in physical memory. And that's going to be 2 to the 12 page frames. And so that is representative or corresponds to how many bits that we have in the page frame number. And so we have our virtual address space, and that's what the process or the ISA are able to see. They see the virtual address space that is available. And with regards to the physical memory space, we've been able to incorporate a broker that can provide for translation from the virtual address space to the physical space in memory. And so to recap, you will start out with your virtual address. And you want to keep in mind that the page size is going to be represent the offsets, the number of bits in the offset. And keep in mind also that this is always going to be represented as a power of 2. And then we also have our physical address space as well. And with this, we can represent it. We have the PFN as well as the offset. And the offset between the virtual and the physical will be the same. And then we want to make sure that we make use of the top part of the address in order to represent the page frame number. And we know that however many bits are used are going to be whatever is left over after we've used the offset. And so with this, we know we'll have the page frames that are going to be used. And you just want to keep in mind that page frames are going to just represent logical chunks of data. And it's going to be, in this case, a physical memory that can store large chunks. So you can think of it in a way as a cell that can be used, or books on a bookshelf that are stacked against each other. And so with this, we know we're going to have two to however many the size of the virtual pages that we're going to use. And so that's going to be representative of the maximum address that we can have. And so we know that if we have 32 bits, we can compute 2 to the NV to see how many addresses there will be. And so even when including the offset, we know that we can have the same amount of memory virtually. And so with physical page frames, it's going to be represented the same way, in that we're going to have 2 to the NP for the physical page frames. And we know that that's going to be after how many bits are used with our offset. So with this in mind, you want to keep in mind virtual pages 2 to the NV, physical 2 to the NP. And so this brings into consideration that very, very rarely will these values be equal. And so that's an important factor that should be taken into consideration. And it's determined by the ISA that we use. And so, no, actually, and so the physical memory space, of course, is going to be what controls how many physical page frames that we'll have. And unlike the virtual pages and the physical page frames, we'll always have the same number of virtual page size and physical frame size. Now, an important question is to consider is, why is page size and frame size going to be equal, but the number of virtual pages and physical page frames are not going to be equal? So you want to keep in mind that we want to keep these equal so that we avoid external fragmentation. And that process for our virtual page is we start with the virtual page and we'll have our offset. And so we'll have that offset of 400. And we know the virtual page number is going to be 1. And so what happens when we do the translation is that we know that the offset is going to be the same. And then we'll need to use a page table to decide what is needed. And so we take the address of page frame 5 here. And that allows for us to determine where we're going to need to pick up with the appropriate translation that we want to use. And so we go to 5, and then we do our offset of 400 to get the physical location. And so let's consider where exactly is the page table going to be located? Where in hardware or software is it going to be represented? Where exactly would it go? Well, we're going to need to put it in hardware because likely it's going to be very big. And it's going to need to be used a lot. So that means that it's going to need a location that allows for quick access. And so in order to make use of the page table in an efficient manner, that means that we're going to have to put it into physical memory. And so how many page tables are we going to need? And how can we determine that? So let's say that we have process 1, 2, 3 to N that is in memory. How many page tables are we going to need for each process? Well, essentially, we're going to need at least N page tables because we're going to need as many page tables as we're going to have processes that are running. So we'll just have as many page tables as we have processes. And so in physical memory, we need to represent where it's going to be stored. And typically what we'll do is we'll try to make use of appropriate usable spaces for the process. And so what we want to do is we'll have our frame table that gets incorporated. And then we'll have page frames for user programs that are also within memory as well. And so what we want to make sure that we make use of the operating system memory manager to provide appropriate abstraction and make sure that it is providing for a place for our page table to work appropriately. And so this is the visual depiction that we have for representing the page tables in our operating system. And so we'll have a page table for each process. And you want to keep in mind that we have this because we're starting each process at a virtual address space 0. And in order for us to accomplish that goal, we need a page table for each process. So how is this utilized in the LC2200? We're going to need one new register that we can use, the PTBR, and this is going to hold the base physical address. And then we're going to need a way to look up the page frame number from the page table for each memory reference that we're going to utilize. And so to update our PCB, we're going to provide for an additional component for PTBR to be represented. And that provides us with a update to represent our appropriate page table.